In this video, we consider the concept of latent instability. If a parcel of air in stable equilibrium is subject to a large vertical displacement, it may eventually become warmer than the environment and therefore unstable. This is opposed to static stability, where parcels are given a small vertical displacement. An atmospheric layer in which a parcel of air eventually becomes unstable due to forced descent is said to possess latent instability. We can assess latent instability on an F160 by plotting the pseudo-wet bulb temperature profile, and then draw a tangent saturation adiabat, and that's a saturation adiabat that just grazes the temperature profile. Latent instability exists for those layers below the tangency point, where TSW is to the right of the tangent saturation adiabat. So what does this look like? Consider a temperature profile, the solid dark line, and the dew point temperature profile, the dashed line. If you lift parcels to saturation from every pressure and bring them back down to the original pressure, you get the wet bulb temperature. And so calculating the wet bulb temperature at every pressure level, we can build up the wet bulb temperature profile like so at each and every pressure. Then we mark in the tangent saturation adiabat, and you can see it's the saturation adiabat with the lowest temperature that just grazes the temperature trace here at point Q. Now consider parcels of air on the wet bulb temperature profile to the left of the tangent saturation adiabat. Parcels lifted along from this curve will follow a saturated adiabat, and the saturated adiabat along which they ascend will never cross the temperature profile. Whereas parcels of air lifted from the wet bulb profile to the right of the tangent saturation adiabat will ascend along saturated adiabats that eventually cross the temperature profile, become warmer than the environment, and therefore are unstable. So in this case, below 860 hectopascals, parcels of air are said to be latently unstable, because eventually they will cross the temperature profile and become unstable. On this figure here, we see an example on the left where a surface parcel has no latent instability. The tangent saturation adiabat is marked in green, and the wet bulb temperature for the surface pressure will move along a saturated adiabat represented by the red dotted line. This line is to the left of the tangent saturation adiabat, and indeed to the left of the temperature profile, and therefore no amount of lifting will release instability. Compare that to the figure on the right, where the tangent saturation adiabat again is marked in green, and we've got a wet bulb profile marked in red. The surface parcel possesses latent instability because as it lifts along a saturated adiabat, it eventually crosses the profile. In fact, we can see that below 750 hectopascals, the atmosphere contains latent instability because all parcels of air below 750 hectopascals, the wet bulb temperature lies to the right of the tangent saturation adiabat. Exercise 3. Plot the temperature profile and classify the layers according to their static stability. Then plot the dew point profile and the wet bulb temperature profile and identify layers as unstable in a latent sense. As a hint, when you calculate TSW, once you've marked in the dry adiabat and the mixing ratio line up which the parcels move, and the saturation adiabat along which the parcels move back down to the original pressure, you want to rub them out. So pause the video now and complete this exercise, either as an exercise now or as homework. So how did you go? Here we have the lower parts of the profile, and the green line is the temperature profile. The red line here is a dry adiabat, and the blue dashed lines represent saturated adiabats. You can see in the lowest layer it contains conditional stability or instability because it's approximately a dry adiabatic lapse rate. Parcels must be saturated. Again, for the second layer and the third layer, there's conditional instability, and indeed the fourth layer. It's not until we get to the fifth layer that we see that it's absolutely stable, because parcels of air moving along that blue saturated adiabat become cooler than the environment. For the upper part of the atmosphere, we see an absolutely stable layer, and then approximately neutrally stable layer, where the temperature lapse rate is about that of a saturated adiabat. Finally, the top of the atmosphere here is absolutely stable. Here are the values plotted of the wet bulb temperature, and you'll note there's an error in the plotting of the wet bulb temperature at 500 hectopascals. The value in the table is correct. You can see that the tangent saturated adiabat touches the profile, actually grazes it in the region of atmosphere that approximates the saturated adiabat, so it doesn't just touch at one point. But you'll see that the wet bulb profile as plotted is to the right of the tangent saturated adiabat below 900 hectopascals. So we say that the layer of 1013 to 900 hectopascals is latently unstable.